from here, I'm going to go through a tour of the product itself, what it looks like, and describe some of the aspects of its operation. So this should be a very familiar screen to most people who've run VMware. This is the home screen of the vSphere client. We ship as a single virtual appliance. Okay, so when you download our software, what are you downloading? It's a virtual appliance. Now, some people get confused and think we're a virtual storage appliance. No, we aren't. Our virtual appliance is not in the data path. You don't have to reconfigure things to point to that virtual appliance. What our virtual appliance is in fact the web server for our user interface. So our user interface is entirely web-based and fully integrated with vCenter and vSphere. But the thing that's actually serving up the web pages today is in fact a vApp. Going forward, there will be direct integration with the new web-based client from VMware. Okay? But another way of saying that is that we don't require a Windows license. We don't require an SQL license. We are self-contained in terms of our administration. Okay? When you deploy that virtual appliance, there's a little bit of one-time configuration that you need to do on the virtual appliance. You need to set up its networking, right, so that you can reach it with a browser. Once you've set up its networking, it can register itself with vCenter vSphere, and then you're back to the standard home screen of vSphere, and we present ourselves as a plugin under solutions and applications, just like practically any party software application. So once again, there is a very minimal one-time setup of the virtual appliance. The virtual appliance is just to host the user interface, to register itself and its extensions and plugins with VMware, not in the data path. And in fact, if you don't want to use our GUI, once you've installed it, licensed it, you never have to run it again. If you in fact had clicked on that Proximal data icon under the Solutions tab there, it would bring up this screen. This screen shows the main functionality. In this case, the screen had just been captured after a live install, and it shows down below in the status screen that the VIB was pushed out and did not require a reboot of the host. We allow you to push the VIB out to your hosts via that install software button right on the screen. We also publish the command lines if you want to do it through scripting. Anything that can be done through our user interface can also be done through scripting. As I said earlier, there are very few things that are required of the virtual appliance. One is that it's the depository for the VIB itself. It's how you actually enter the license information, and it's how you define the cache partition. But other than that, once you've done those three steps, it is not a necessary component of our solution. This screen represents the top of our main UI within vCenter. This is the host level view. There's a couple things I'm going to point out on here. The first is the pie chart. The pie chart represents a real-time look of how information is flowing through the system. Green represents cache hits. So you can see there was a very large percentage of cache hits. Reds are cache misses. Those are reads that actually had to be satisfied by the backing store. There's a very thin blue sliver on there. That is a write around, and then the goldish color is write through operations. Across the top, you can see that There are a number of tabs here that allow you to specify whether you want a view of real-time information, the last day, the last week, or the last month of operation. On the bottom, there are a couple of bar charts. I'll be talking a little bit more about them, but in the host view, the top bar chart is cache device usage by device. So if you had multiple storage devices with multiple data stores attached to your host, this would show you which data stores were using what percentage of the cache resources.
You support multiple PCIe cards or multiple SSDs in a server?
Yes, we do. And in fact,
you can concatenate as much storage as you carve out for your cache.
And we will actually essentially spread the load evenly across them. The bottom bar chart is cache usage by guest. This allows you to see which guests are using what percentages of the cache resources. A couple of controls down here. Cache state. This is the host level cache state. By default, once you install the VIB, the cache is enabled. You can take the cache into one of 4 states. Enabled is the normal state. The next state over is locked. In the locked state, no new entries will be allowed into the cache, but the cache will be kept coherent and the cache will serve data. And so if you were doing some sort of one-time process where you did not want to disturb the current cache state and you knew that it was going to be doing a lot of I/O that had the potential for disturbing the cache state, you could lock the cache down, run that process, and then unlock the cache.
Like if you didn't want to cache backups or something like that?
Correct.
Or virus scans or something, yeah.
Correct. Of course, our Glimmer list would already do that for you,
yeah.
But it's illustrative of the type of thing that you might want to do that for. The next state is offline. In the offline state, the cache is kept coherent, so any writes that would affect the contents of the cache will in fact update the cache, keep it coherent, but no data will be served out of the cache. The offline state is actually very, very useful for demonstrations, and we'll be talking about that a little bit later because it essentially allows you to turn off the cache and see what the difference is in the system throughput and performance, and then instantly turn it back on and be right where you were. The final state, disabled, pulls us out of the picture. So it does not keep the cache coherent. In fact, it flushes everything, and we're not processing the I/O.
What are the squiggly line graph on top? What does that represent?
Oh, we're going to be talking about that a lot. So
all right.
If you can hold on for just about 10 minutes, I think we'll be there. This is the same screen, only we've scrolled down to the bottom of it. And this is listing the devices associated with this host. Interesting things here, of course, all the devices are enabled for caching by default, but you can disable devices. So you can essentially implement caching policies by data store. You could have data stores on one device that is cached, data store on another device that's not cached, implement 2 different service levels that are determined by which data store you deploy your guest against. If you were to be able to read this, it's kind of an eye chart, you could see that RDM devices are in that list. We can cache RDM devices, which is fairly unique in this space. If you were to be able to read this, you'd see that we have DAS device, an iSCSI device, an EMC, a NetApp, as well as some RDM devices all there, all cacheable by default, but can be individually controlled. This screenshot is subtly different than the last.
Name is different.
There you go. It's a PerVM view. On the far left-hand side of the vSphere client is a tree view control that allows you to select either hosts or individual guest machines. The previous screenshots had all been with a host selected. This screenshot is with an individual guest selected. It is subtly different for a couple of reasons. Number one, the devices are associated with the host, not with an individual guest. However, You can enable or disable caching on a per guest basis. So we do allow fine-grained control over cache functionality. Once again, the default state, you install our VIB, everything's enabled, and the system self-tunes. But we do allow people to make exceptions and override there. The reason why I say this is subtly different is because in the series of screenshots that we used for this presentation, there was only one guest. And so the pie chart and the strip chart above are exactly the same because the host view and the guest view are identical because there's only one guest. If in fact there have been multiple guests deployed, the pie chart and the strip chart would be different because this would reflect only this individual guest's I/O flow, right? So you can drill down and see what the different performances are for individual guests as well as the aggregate of the whole host.
Okay, so I can say don't cache this guest or cache this guest,
Correct.
but I can't say cache this guest at lower priority than this other guest.
We will get to that. Okay. Couple more real brief things about the user interface. First of all, I'm colorblind, and so I have this pet peeve about color-coded graphs. And so anything that's color-coded in our user interface, there's always going to be a tooltip on it. In this case, the mouse was hovered over the pie chart, and it popped up the tooltip, which in fact gives you the legend that identifies the cache read rate at 66%, the cache update rate at 28%, the disk read rate, and the disk write rate, representing the pie chart below, both in textual format and with actual percentages as opposed to trying to eyeball it, right?
Okay, but I'm glad Rich talked you out of the varying hash patterns that look like bad plaids.
There you go.
Good for something.
I guess there's a couple other things to note. In this example, because we're going to be talking more about the performance in just a couple more slides.
But we haven't been talking about performance already?
Not
It's a caching solution, isn't it?
Not to the extent that I hope we get into it.
We're talking about density.
But the thing to note is that if you were to sum up the cache reads and the disk reads, you'd see that they sum to 70%. So it's a fairly classic 70-30 read-write ratio in here. The one thing that's sort of non-representative, just because this was a synthetic torture test that was being run here, is that in real life, you would tend to see the blue and yellow percentages roughly inverse. That there tends to be far more right around than right through in real life. Okay. The last note here, this screenshot is
adaptively deciding whether to use right around or right through, or?
So that actually, I wouldn't term it as adaptive. Right through is performed when in fact a write operation overlaps with any piece of data that's already in the read cache. And so we write it through to maintain cache coherency. Okay, and so essentially what happens is the write gets split, there's a parallel update to the flash as well as the backing store, and then you don't acknowledge the guest till both of those complete.
And ghosts and glimmer and those sorts of things don't necessarily interact in that
Not at all.
perspective.
Okay, so the first write goes directly to the backing store, then I read it.
If
then
it's
I write
read,
it,
if
then
it's
I
read.
overwrite it, and that becomes a write
Yeah.
because the data is already in the cache.
Very close. So the first write, nothing happens. The first read, nothing happens. Gets read enough to be pulled into the cache,
Okay.
Ghost or
subsequently
glimmer,
updated and
yeah.
written, then it would be a write through. Okay? This screenshot is odd man out. All right, and it was chosen to illustrate something specifically. So I want to make sure that you realize this is a very unrealistic 100% hit rate. This was taken for a different reason. What it's showing down here is the cache usage by guest and the different shades of blue. You will see that there's a very, very asymmetric, non-uniform distribution of cache resources. If you were to hover over any one of these individual instances, and in this case they've hovered over this instance, it actually pops up a tooltip with the guest name so you can see who it is, and the actual size of the cache devoted to that guest, as well as the relative percentage of the cache devoted to that guest. And once again, it's merit-based. It was that guest deserved that percentage of cache to maximize the overall system throughput. Okay, so just pointing out non-uniform distribution between the guests. Okay. This is where we start talking about improvements, okay? And I haven't really spent a whole lot of time on either the strip chart or this table beneath it. This table represents performance counters for the item being looked at. It's all context sensitive, whether it's an individual guest or the host. This is once again the host view. And it has various statistics: incoming reads, outgoing reads, incoming and outgoing writes, incoming total, outgoing total, and cache hits. And the rows have units, what the latest measurement is, what the maximum and minimums were, and what the average is over time, as well as the color legend that corresponds to the strip chart above. If you actually click on a row in this table, it will highlight the corresponding line in the strip chart above. And in fact, what's happened here is that writes have been selected, clicked on, and then there was a mouse over on reads. And when you mouse over something, that will also highlight that particular line in the strip chart. So this is a shorthand for us to be able to emphasize read performance and write performance for this particular guest. Okay? I want to point out once again, this is that classic 70-30 workload. It is in fact a torture test for our algorithms in the sense that there is no optimal solution for tuning the cache. And that's what you're seeing here is just about the time when the cache thinks it's optimized its performance, the workload changes, and it has to relearn. Okay, so that's why you would see this going on and on and on. As time progressed, you'd see a series of peaks as the workload changes and it re-optimizes, and the workload changes and it re-optimizes. Read performance is the top highlighted line. Write performance is the bottom highlighted line. And let's talk about that gap right there. That gap was us taking the cache offline. Okay? So this is the what if. A job started up. These are the read and write rates associated with that job, thanks to the benefits of our caching.
It's a stacked chart, is it? Stacked chart because it goes nicely together?
No, it isn't. In fact, the stack chart is this higher light line, which you can barely see on here. It is because there's dependencies between the reads and the writes. There's some synchronization of the load. Okay? So, the read rate, the write rate, the interesting thing is we took the cache offline here and let it offline for a while, then we turn it back online. What does this show you? Well, it shows you that if you looked at the read rate here versus the sort of steady state read rate here, we doubled the read rate. It's maybe 2.5 times the read rate for this workload. But equally interesting is the write rate. We got a very substantial write performance increase, even though we're a read cache. Why is that? It's because the writes aren't competing with as many reads for the heads of the disk and the controller of the shared storage. Okay? So this is to say, a lot of people say, what about writes? Well, actually, there are very measurable performance improvements for writes with a read caching strategy. This next chart is highlighting, once again, the read rate as well as the outgoing read rate. And this is the reason why we got the write improvement. Very few reads were actually making it out to the array to be in competition with the write workload. And of course, you would expect that when you turn the cache off, the outgoing read rate and the observed read rate would be identical, right? Because the cache can't
So why wouldn't
offload
you see that activity, that level of read rate going out at the beginning of when you're warming up the cache there? Why wouldn't you see that sort of thing, and then now it's sort of plummet as cache started to take over? You know what I mean? So up until that point where the knee of the curve is, you would think there would be an outgoing read rate which would be relatively the same level as that other line.
And that's because this is not a real world
This is not
test.
a real world activity. Yeah.
And chances are the engineers had been running this test previously. The cache was essentially pre-warmed. But you're exactly right. It takes a short while. It usually takes on the order of 5 to 10 minutes to warm the cache.
It's not a running workload where they enabled the cache. The cache was already on. It was a used environment, right?
Yeah. They didn't start from a clean page.
Yeah.
Thank you, Hans.
And then once again, you're asking about the stack chart. This is in fact the stack chart here showing what the overall system throughput is. Okay, so at VMworld this year we announced a Hyper-V product, and it's okay. It's a virtualization show.
That's when you can.
There you go. And we are expecting December GA on this. And you may not be as familiar with Hyper-V and the virtual machine manager within Microsoft System Center. So this is just a little bit of highlight for those who aren't as familiar with it. This is the main pane of the virtual machine manager. Home screen, an individual test machine has been selected. We populate the AutoCache host level stats button has been selected. And then, once again, the enabled, locked, offline, disabled. And this should look remarkably similar. The same table down below, the same statistics, the same pie chart. The look and feel has adopted the Microsoft sort of flat pane, muted palette.
Ugly crap.
That too. But it is, in fact, the same functionality. Right?
Look, John's not here. Somebody's got to defend these guys.
So,
Yeah, where's Obedo when you need him? He's probably not even watching the video.
I have like a little personal rant here, and that's how do you make sense of all the different claims in the world for competing products here? And this is really my view on what people should be looking at when they're evaluating caching. First and foremost, caching is all about probability. And your results are going to vary, and they're entirely workload dependent, and no one can tell you beforehand what your results are going to be, right? Benchmarks are so terribly abused. They're very good at characterizing devices. They're pretty bad, actually, at characterizing cache performance. And, we're guilty of using Iometer just like everyone else uses Iometer. But Iometer, I guarantee you, I can make Iometer show whatever results I want it to show, right?
So can I. I do that for a living.
Yeah, we know.
Iometer is the absolute worst workload generator, because I won't be so kind just to call it a benchmark, because it's not that, for caching, because it does sequential and it does random and it never generates a hotspot.
There you go. It is, in fact, very difficult to simulate production workloads with benchmarks and synthetic load generators. You want to know what a product's going to do for you? put it in your test lab, run your data through it, right? The closer you get to your real workloads, the closer you get to your real storage configuration, your real environment, the more meaningful your results are going to be. We have designed a product that we will gladly put head-to-head against anyone else's product. And
it's non-disruptive.
And it's
You
non-disruptive.
can install it. There's no reboots whatsoever. Okay.
Correct.
I mean, something's got to be done with your SSDs, right? I mean, if you've got data on your SSDs, those you've got to somehow carve out some space for the cache, right?
Another couple of points.
That's not disruptive. I mean, there's no
That's true.
there's no guests that need to be rebooted.
That's true. I agree. I agree.
Steady state is different than initialization, right? Cache warming is one aspect of it. Garbage collection, wear leveling is another aspect of it. Large caches can take a while to really fill. And so, be wary of 30-second benchmark runs. A lot can happen in steady state that's very, very different than a fresh run on a fresh device. And truly, beware of anyone who's claiming hundreds or thousands of times performance improvements with these caching strategies. It's possible. It's just not probable.
Well, all you have to do is install Virident's 4.8 terabyte PCIe card and run a 100 gigabyte LUN on it.
Yeah.
Or even a 4.6 terabyte LUN.
Yeah, well,
If the data set the benchmark's running against is smaller than the SSD, you get completely unrealistic results.
and that brings up a painful true experience for us in an evaluation. We had an evaluation where someone claimed, we don't seem to be getting any benefit. And when you looked into what had happened, they were running iometer, and they were running it in file system mode, not in device mode. And their file system was almost full, so the iobw.tst data file that iometer runs against was approximately 5 megabytes and fit entirely in the RAM cache of their array. And so when they were comparing the RAM cache of their array to a flash-based cache, they didn't see a great improvement. And I understand that, but I don't accept that as a valid test. So once again, if people are claiming hundreds or thousands of times improvement, you should really, really scrutinize that. Hit rates are everything with caching solutions, okay? But along with hit rates are inter-IO dependencies. And this is something that, once again, we mentioned earlier in that graph that we were showing that there was interlock between the reads and writes. Interlock is real. There are very few applications that generate data without first reading data of some sort. Okay? Therein lies the problem. If you have to read something before you write it, then your writes are actually affected by read latencies. And so, I have seen some caching demonstrations that have been highly suspect because, in fact, there were no inter-IO dependencies, and I am going to do that for you right now. Seen this graph before? I think you have. It should look very familiar. It's the same one we've been talking about for about the last 40 minutes, right? So this is a 7030 workload with dependency between the reads and writes. There's some interlock between these two operations. It's been running for a while. It's on test 0. It's a single virtual machine. I'm now going to show you the exact same graph. That exact same graph, if you could read the time along the bottom, is right there. It's been squashed down to nothing. Why has it been squashed down to nothing? because I removed the dependency between reads and writes. And so, the exact same workload, exact same storage infrastructure, real-world type conditions with dependencies between reads and writes, getting about 4,200 IOPS. Same hardware, same workload, remove that dependency, I'm at 101,000 IOPS, right? You're never going to see that in the real world. Right? So, once again, almost all applications, in fact, have interlock between the reads and the write operations. Therefore, unless you can guarantee 100% hit rates on your reads, which I'm here to tell you, no caching solution can guarantee that, you're going to be affected by the disks and not get those hundreds of thousands of IOPS.
Sorry to interrupt you again. We have someone listening and just showed me a screenshot that he has to shut down the guest before NFS caching can be enabled. So you just said there's no interruption, there's no maintenance modes, but there is.
So, this is a situation where the host has not been shut down, the host is running. The individual guest for an NFS client had to be either suspended and resumed or restarted.
So there is a maintenance mode for the guest.
If you're running an NFS data store in that one particular situation, yes.
Yeah.
And once again, that is a limitation that was forced upon us. Yeah. So, flash caching in perspective. Where do things go? What are our views? Flash is in the very early stages of adoption in the enterprise. It's been a very long road. Many of us have been waiting over a decade to see this happen. It's starting now. There are not any single solutions that are going to meet all needs. And in fact, I believe that caching, and in particular flash-based caching, and as well as flash-based tiering, are going to be present at all levels in the data infrastructure for different purposes. Okay? So we firmly believe that a modest amount of flash in the host as a read cache has the best price performance, the least risk and impact. There are applications where write-back caching in the host does make sense, as long as you're aware of the fact that write-back caching is not a panacea. It cannot handle or help you if you're fundamentally write-bound. It's an impedance matching technique that can absorb bursts of write activities and dole them out over time. And once again, if you have a situation where you have bursty writes that are not dependent on reads, it can provide some pretty good results. And so we do believe that there is a use case for that. At larger scale, we believe that there's a very valid use case for shared storage-based flash, either in terms of caching or tierings. Once again, this will be a higher cost solution. But the fact of the matter is, if you're going to do caching on writes and you care about your data, you have to have some form of replication. Once you take it off box to ensure data availability, it doesn't much matter whether you take it host to host or host to storage. You're paying the same sorts of round-trip latencies. You know, we try very hard to be as efficient as we can within the kernel, and we're very proud of the fact that we turn around flash reads in tens of microseconds. On a good flash PCIe card, we can handle hits in 20 microseconds, okay? With less than 5 microseconds of processing. You're wondering about what does it take to do those glimmer lists and the indexing and the hashing and all that stuff? Well, the fact of the matter is it can be very, very quick and efficient. When you go off box, whether you're talking about fiber channel round-trip latencies, when you're talking about Ethernet round-trip latencies, you can easily be in the hundreds of microseconds. So there is a price to be paid for replication of data, right? And if you're going to pay that price, it may make sense to, in fact, pay that price to your storage, where, in fact, you can be transparent to snapshotting, VAI.
Yeah, unfortunately,
clone,
that assumes my
offload.
storage is worth installing Flash in.
Well,
But the extend the life of my crappy old storage use case, it might be the exception.
right. And as you well point out, if the future goes to vSAN, it probably doesn't make sense to do write-back caching on top of vSAN, right? I would agree with that 100%. So what's next? Where do we go from here? Well, this is a bit of a tease, to be honest with you. I certainly can't talk specifics about unannounced product, right? That's kind of a cardinal sin. So
Sure you can.
okay, I can do that just for you, and it'll be off camera. How's that? But what I can do is state directionally where we're going as a company, right? So what is our vision? Our vision is policy-based management and processing of I/O within hypervisors, right? That policy needs to be fine-grained policy down to the virtual disk granularity. We need to be able to process based on that policy, monitor based on that policy, report based on that policy. This is what we mean by I/O intelligence. And for those of you who've actually been following our company for a while, you'd note that our tagline changed late last year, early this year to I/O intelligence. We are using the technologies that we developed to implement caching to go into other areas of I/O processing and management. Caching is just the beginning for us, right? We've already developed this policy-based engine and applied it to caching. And that's our first product. I'm here to tell you that next year you're going to be seeing some pretty exciting announcements for us on future products. Okay. That's it for my presentation. Thank you very much.